else wants to record, just let me know and I'll make you a co-host. I don't think you can record without it.
Okay, I'm recording right now, so should get it.
All right, let's see here. Let me do one thing. I had to pull up OneNote again. There's still some updates going on this computer, mainly because I haven't used Zoom in forever. And I mean, I haven't used it for teaching, and I have to do updates for this document camera. Let's see here. All right, I'm going to do something. So for this quiz, I just wanted to mention this was not meant to be tricky or anything. I based it on something I put on the board that Chase asked me about. Are you here, Chase? He's not here. He's one of two people missing. Anyway, here's what it boiled down to. The quiz, and I'm just going to go through this kind of quickly. Matter of fact, I'll tell you what, I'm going to share this one screen. I'm going to share this screen for a second. Now, can you all see the quiz right here?
Yeah, I can see it.
All right. The only thing I'm going to do here is just mention something. When you have two charges, one is 1 microcoulomb, it's -2 meters. It's located at the y-axis. The other is 3 microcoulombs at 4 meters. And where should you locate a third charge on the y-axis between the two charges? There's solutions outside this, but between the two charges, the only thing you're going to do is set the electric field equal to 0. Does that make sense to everybody?
Yeah.
Okay. Next, if that's the case, the electric field from the first charge, Q1, will be Q1 over K, and K, of course, is going to be, it's not shown there, but 4 pi, 1 over 4 pi epsilon naught. It's 9 times 10 to the 9th. And because it's between the two, this charge is located at -2, so the distance difference between the first one and the second one would be y, or it would be Q1 K over y plus 2 squared, because normally it'd be y minus 2 if it was located plus 2, but since it's -2, it's that. And then the second electric field that will be in the opposite direction will be Q2 K over y minus 4, because this one's located at +4. And of course, this field will be negative. So it means that E1 plus E2 would be 0, or E1 is equal to E2 in magnitude. You all follow me on that, class?
Yeah.
Now, if you take a look at that, and I'm gonna go back to the answers are there and they're right, but and a bunch of people got it right, but I want to just do this for you. So I have to go to a new share and document. All right, now I hope you can see the document camera right here.
Yeah, we can.
Okay, so then if I'm going to do this, so I have, and this may not show up real well, but I'm going to try my best. It has an autofocus, but it doesn't always pull it real quick. So here it's E1 equals E2, and E1 is really Q1 K over, and this is going to be y plus 2 squared is equal to K times Q2 over y minus 4 squared. So just going through that, one of the things you can see, and here I'm equating the two field strengths. One is going to be opposite the other. I can cancel K. And now when you get at this point, and it depends how you want to do it, You can actually say that, well, if I do this, Q1 is equal to 1 microcoulomb, and that in Q2 is 3 microcoulombs for the first part. So really, it's equal to 3Q1. So I'm going to just put it here. I'm going to have Q1 K over here, and Y plus 2 squared is equal to, and here I'm going to, well, I already got rid of the K, so this is going to be 3Q1 over Y minus 4 squared. Obviously, the Q1s cancel. What I'm trying to do is make it as simple to see as possible. Now I just cross multiply, so I have Y minus 4 squared is equal to 3Y plus 2 quantity squared. I'm sorry, 3 times Y plus 2 quantity squared. Can everybody follow what I'm doing?
Yeah.
Are you good with this, everyone? And you can unmute yourself and put yourself on the overhead if you want, just to make sure. So now square this out. So I have Y squared minus 8Y plus 16 is equal to, and I'll leave the 3 here, and then I have Y squared plus 4Y, and this is going to be plus 4, and all this is multiplied by 3. So I have 3Y squared plus 12Y plus 12 is equal to Y squared minus 8Y plus 16. Now I just collect terms. I'll take the Y squared on this side, so 2Y squared over here. And then I got minus 8Y and 12Y is plus 20Y here. And then I got 16 plus 12, so it's going to be minus 4. All that equals 0. Everybody with me on what I'm doing and why I'm doing it, class?
Yeah.
Okay, then simplify if you want. Make it Y, just divide by 2 plus 10Y. I think this is the way most of you guys who got it right did it. Equals 0. That's a quadratic. And the general solution is minus B plus or minus the square root of B squared minus 4AC over 2A. And that will be the roots. There'll be 2 of them in general. So B is the coefficient of single Y, so it's minus 10 plus or minus the square root. B here is 10, so it's 10 squared is 100 minus 4 times A is 1. C is minus 2, so it's really plus 8 here. And it's over 2A, and A is the coefficient of Y squared, which is just 2. So that's minus 5 plus or minus the square root. And you can leave it as 108 over 2. And when you get there, you're going to get 2 roots. The root that actually satisfies the solution between the 2 is going to be at 0.196. Everybody with me on that, class?
Yeah.
Yeah, some people probably overthought that one. That was not meant to be tricky. The second part is just finding, let's see if I can do it here. Well, I'll just say this. The second part is finding finding the force on a charge that's located at 5 meters. And the only thing you're doing there, you got Q1 here, and it's at minus 2 meters, and this is the y-axis. Here's 0, and then you have a charge located at 5 meters, and you have another charge down here at 4. They're both positive charges. Here's Q2. And if you want the force on this third charge, only thing I'm going to do is find the electric field at this point and then multiply it by the value of the charge. So the electric field at this point at Y equals 5, both of them, they're both positive. So it's K, then it's going to be Q1 And here it's going to be, and I think some of you just put down 7. So it's the position here is 5. The position here is -2. 5 minus a -2 is 7 squared plus KQ2 over, and 5 minus 4 is just 1 squared. And that will be the electric field value. And then if you take that electric field times the charge, which is Q3, you're going to get the force on 3. Does that make sense to everybody, class?
Yeah.
So we'll
Yep.
mess
Yep.
it up. Everybody follow me on that? Now that's the only thing that's required. I think the biggest problem is people overthought the first part. The second part was straightforward though. You just got 2 charges and get it. So anytime they want the point where the force is 0, the field is 0. Okay?
Hey, Dr. Baginski.
Yeah.
When's our next quiz gonna be?
I wish you didn't ask me that. Because of the inclement weather, I think I'm going to do it on Wednesday and give you, because Friday we're not meeting in person. It's a bit awkward. Is that all right, everybody?
So that's gonna be our, are we gonna just do a quiz and then review, or review and then quiz then?
How about I do a quiz and review on Wednesday?
Okay.
I mean, so we'll meet Friday. I'm going to go over some new material. I want you to be there, but I don't think that's going to cause a problem. By the way, I asked my department chair if I could meet online simply because I know with some of the messages that I was getting around 8 o'clock in the morning, I had a 9:30 class. They were talking about serious threat of I guess there was a tornado somewhere down south already. I don't know how much bad weather, and we're not out of the storm yet. There's more storms. How many of you guys are on campus, by the way?
I'm not.
I'm not.
Smart move. Anybody else on campus? There were a bunch in my first class that were on campus. You are, Jonathan? All right. Well, I don't know. And frankly, I would rather you're not on campus because we're still supposed to get some fairly serious bad weather shortly, I think, unless they changed again. Hold on. But I mean, there's some bad weather already. No hail though. That's what I'm really worried about. All right. So that's that. Now I'm opening this book, my textbook, your textbook, and I'm going to let's see. Any other questions before I get going on this lecture?
Like for the homework?
Yeah, sure.
I had one.
Mhm.
It was the last one. 3.48.
All right, let me just put it up here so everybody can see. 3.4. I wish this autofocus I could change. Hold on. Maybe I can. I have to go to the camera app thing. Tell you what, I'll just work with it. I'll mess with this later. So this was on my morning class. It was giving me fits too. I think I can magnify it right here though from maybe not. What is this start focus mode? Not that one. There's a way to get this thing to increase in size, but for now, I'll just have to work with this. So you said 3.48, right?
I did. Yeah.
All right, find the electric field at a point resulting from a surface charge density existing on the Z plane, Z equals 0 plane, that's the XY plane of that, and from, okay, this is a disk. It's a hollow disk. Assume V equals 0 at a point of infinite distance. So they want the electric field. We're going to get the voltage first, then we're going to get the electric field. You all follow the reason behind it?
Yeah.
All right, because minus the gradient of the voltage is the electric field at static. So this is kind of a cool problem. So I'm gonna do it in parts here, and hopefully you can see it. I wasn't expecting to use this thing for a long time, but I'm glad I kept it. So here's what I'm going to do. First, we're going to talk about if we just have, if this is X and this is Y, and this is a distance Z up, and we have a ring of charge as before. You all remember the ring of charge, right? So, I mean, a charge, it's going to have rho L. So it's going to have a radius here, and I'm going to use the radius of rho, and it has a charge density of rho L. That will be in coulombs per meter. And I want to calculate not the electric field, but the voltage at this point. So I want V at the point Z. Now, is everybody following what I'm trying to do?
Yeah.
I'm glad you're talking. It's much easier to see that than look at that screen because I got to almost look through this overhead camera. So if I want that right there, if I want the voltage here, what I can say is if I have a differential chunk of charge, if I call that dq, the differential voltage from a differential chunk of charge, assuming at infinity, the voltage is zero, and that was stated in the problem, that's simply just dq over 4 pi epsilon naught, and it's simply divided by this radius vector, the distance r to that point. R here is simply equal to square root of Z squared plus rho squared. So it's going to be just the square root of rho squared plus Z squared. That's the differential voltage. Y'all with me, class?
Yeah. Yeah.
I mean, everybody okay with this? I'm just showing you that would be the differential voltage. Well, what is the differential charge? Well, I gotta push this away. I hope can you all hear me though?
Yeah. Yeah.
Okay, dq is equal to, well, now you got to take the differential length, and that's equal to, in this case, it's a rho, because I'm using rho, and it would be d phi times rho L. This would be the differential length. That's the charge density or line charge density. So this would be the differential amount of charge there. So then I can say that dv, you're going to like this too. It's easy. dv itself is equal to dq, which is rho d phi, and I'll put rho L in front. All right, that rho L there is the charge density. Make sense to everybody?
Why is DQ rho D phi rho?
All right, this is a differential length, right?
Okay. I get it now. Yeah, that's good.
It's really
Is that differential? That's differential arc length.
Yep.
Okay,
It's
I got it.
length. It's
Thanks.
and I always think of a windshield wiper's track on a differential angular movement. The tip of that windshield wiper will always be proportional. The movement will be proportional to the length of the wiper over times the differential distance. Now, since I'm going to put dv. dv is dq, that's dq over 4 pi epsilon naught. And here it's going to be square root of rho squared plus Z squared. You all agree with that?
Yeah.
Now I have to integrate that around the loop. Just notice this. V itself will be equal to, technically, it's the integral of dv from 0 to 2 pi, because the angular integration is over phi. And take one moment to look at this. Nothing inside here depends on phi except d phi. So it's simply 2 pi. Y'all follow me in this class? I'll write it down.
Yeah.
0 to 2 pi of rho L times rho d phi over 4 pi epsilon naught. And here you're going to have the square root of rho squared plus Z squared. Those are both constant. Well, that's just multiplying it by 2 pi. So I can say that V of Z would be equal to, and check me out on this, this is going to be simply, the integral of d phi is phi from 0 to 2 pi, brings out a 2 pi. So this becomes rho L over 2 epsilon naught. And then it's going to be divided by square root of rho squared plus Z squared. Y'all with me on that, class?
So you said row's constant, but it goes from 2 to 6.
We're just
Unless we're
doing
not
a
there
loop.
yet. Okay.
I'm not,
Okay.
this is just for a loop.
Yeah, okay.
And I want to show you how easy it is to get the E field from that, by the way, on the Z axis. Do y'all agree it's just going to be in the Z direction?
Mhm.
All right, well, now if this is the voltage and you want the E field, all right, you simply take the gradient minus the gradient of the voltage. Well, if you look in the back of the book, this is Z right here. I mean, you can use Cartesian or you can use cylindrical. It'll get you the same thing. That's just going to be equal to its minus d dz of this rho L over 2 epsilon naught. And this is really going to be, well, I can write this as rho squared plus z squared to the minus 1/2 power. Do y'all agree with that?
Mhm.
All right, take a derivative. What do you get? Now, when you take a derivative of this, you're going to get, I'll put the minus sign here, you're going to get rho L over 2 epsilon naught. That stays in front. Then the derivative of this is going to be minus 1/2, right? Then it's the derivative of this with respect to z, or it's minus 1/2, sorry. And it's this to the minus, this is going to be what? When I take the derivative of
It'll be to the minus
this,
3/2.
that's right. Or I can put rho squared plus z squared to the 3/2 power. And then I have to take another derivative in here with respect to z, and I get 2z. Now, what you can see is it's in the AZ direction, by the way. The other derivatives, they're ineffective. It's on the Z axis. So
Hang on.
this,
I have a question.
go ahead.
Earlier when you got did the integral for the voltage, did you drop that row on? Yeah, that row. What happened to it?
It was dropped. My
Okay,
bad.
just making sure.
Sorry about that. But it should have been just out in front. That's what I should have
Yeah.
done. All right. You're right. So there should be a row here too. My bad. It has to be there. It's my bad. Y'all, are you with me though?
Mhm.
So go ahead and multiply that through. So I get E equals the minus minus is plus. And now you can see this 2 and that 2 cancel. So I get minus, or I get rho L, that's positive. Then I get over 2 epsilon naught here. And then I have rho, right? And the Z stays, the 2 cancels. It's rho times Z. And it's in the AZ direction. And it's divided by rho squared plus z squared to the 3/2 power. By the way, you'll find that's the exact result we proved by integrating the electric field strength and then making arguments about symmetry in the horizontal direction. Do you all remember that?
Yes.
I'm making sure everybody's with me. And y'all can see me okay?
Yeah.
Or see this? I know it's a little bleary and I wish I could do something like that. Focus. I'm going to try one last thing with it because I thought I could. Devices and settings. Give me 1 second. I know what this is, but it's a camera. Properties. Well, I don't think I'm going to get anywhere with this. I have to find the actual download for this camera thing. It's not automatically finding. Anyway, that's the electric field. So now, coming back to this is the thing that we found is the voltage, right? That's for a single loop of wire with a charge density, right?
Yeah.
So instead of having a single loop, I'll make rho L equal. Now I'm going to make this thing have some fatness, you might say. Now it's going to have a differential thickness of d rho. And now instead of putting rho L here, I'm going to put rho S ds. Do you all follow me? I mean rho S times d rho. Pardon me. You with me on that?
Yeah.
Okay. I'm going to have to flip this. So Bear with me. So now when I get that, now I'm going to say for this loop, and I bet you guys see it now. If this is X and this is Y, it says I have an inner radius and I have an outer radius where the charge exists. I'll call it A and B. It doesn't matter what they are. You all with me, class?
Mhm.
I'm at a height Z, whatever Z is. And now what I'm going to do is say, if I have a little thin strip of, I think you know what I'm doing now, a thin slice right here. And I want the differential voltage from that, better use the other marker, at this point right here, dV from this. I think y'all follow me. It's dV, it's going to be a function of Z and rho. I can say that differential voltage will be equal to, and here I'm going to go ahead and say, just as before, I take the differential voltage I got before and I replace rho L with simply rho S times d rho. And then I'm going to have times rho over, and that's 2 epsilon naught. And it's going to be divided by yeah, that's right. Divided by rho squared plus Z squared to the 1/2 power. I think you can see that. And the only thing I've done there is replaced rho L in the prior thing, the actual voltage at that point for just a loop, with rho S d rho. Can y'all follow me?
Yeah.
Now, once I have that, I need to integrate it from A to B. So to get the total voltage at Z, I have to integrate dV from A to B because it's 0 at infinity. And here I'm just going to take the rho S out in front, whatever that he gave. It's a constant, right, for this problem?
Rho S is constant, yes.
If it wasn't constant, it was a function of rho, then you would have a different form of integration. But if it's constant, you're going to get what I'm showing you. So it's going to be it's rho S comes out in front, 2 epsilon naught come out in front. Then I've got this integral. I've got an integral of rho d rho over rho squared plus Z squared to the 1/2 power from A to B. Y'all agree with that? This is a constant.
Mhm.
Can y'all see this, by the way? This is a great question. This is a good problem, too. It makes you actually understand how to, I call it the building block approach, how to use a differential segment of charge to get a differential voltage and then get the integration to get the rest. So for this one, I don't know how Whitworth's book does it, but this is the easiest way. Once I have that, now I'm going to do the integral of this. And now here's what I'm going to do. I'll say that the V of Z here, this rho S, whatever it is, over 2 epsilon naught, just leave it alone. Now, when I do this integral, what I'll do is let U, I think I can do U squared is equal to rho squared plus Z squared. That's a Z. And that means 2U du is equal to, because this is going to be a differential with rho, is equal to 2 rho d rho. You all agree with that?
Yeah.
You could just make, I mean, you could use U is equal to rho squared plus Z squared, just do it that way too. But if you get this, then I'm going to have the integral here. And if you look at this, U du is rho d rho. So it's going to be on top U du over, and this is rho squared plus Z squared to the 1/2, which is going to be really U squared to the 1/2 power, which is just U. You all agree with that?
Yes.
All right. So it's over U. And U itself goes from when rho is equal to A, that's going to be U is this down here is going to be the square root of A squared plus Z squared. That would be the lower limit. And the upper limit would be the square root of B squared plus Z squared. Does everybody follow me on this one? If I'm going to, U would be the square root of this, right? I'm only taking the positive roots on this one. So it goes from square root of A squared plus B squared to square root of B squared plus C squared. Does everybody agree with that part?
Yes.
Now, one thing is obvious, the U's cancel top and bottom. Agreed?
Yeah.
So we integrate du, we get u. So that means v of z, and I don't know how he's formed it, should be rho s over 2 epsilon naught. And the upper one is going to be a square root of b squared minus c squared. The lower one is minus square root of a squared plus b squared. Y'all agree with that?
Yeah.
And as far as I can tell, I mean, we can get a common denominator. Does he have it like this, or does he get something for the common?
That's the V. Yeah, that's exactly what he gets. Yeah. Pretty
But
much.
you can, I just want you to say something about, you can get a common denominator. You can keep messing with this all you want. All right, but that's what's going to happen. One thing I'll make note of, this should be a squared plus z squared. When you allow z to go to infinity, it goes to 0 for any finite a and b. But when a and b are going to infinity, or I mean, when a goes to 0, pardon me, when a goes to 0, in other words, if you integrate from 0 to infinity, that looks like the voltage from a plane. And you'll notice the voltage goes to infinity because b would go to infinity. And that's absolutely true. Here's why. If you have an infinite plane, you have an infinite amount of charge. Do you all give me that?
Mhm.
Not just in one dimension, but in two. So if you measure the voltage between anything and infinity, since you have an infinite amount of charge, you're going to get the integral of the E dot dl to go to infinity as well. And it'll go even beyond infinity. I think it's infinity squared, but I just want to mention that. But that's right. Because I'm all right. Grayson, did you ask this or?
Yeah, I did ask this.
Anybody else have a question about that? That's a classic problem. It's a good problem too, that kind of thing. What I can easily do on a quiz or something like that is I can put in a different value of charge density. Now, this integration was a pretty easy one. Do you all agree? Rho d rho. I mean, we got a u du. The u's canceled. Is pretty much an easy one. But this is a classic problem. Just give you a heads up on that. Okay. Start with the building block approach. Any other questions?
I don't have any.
Guys, I don't like doing it this way, especially since my focus is not what I'd like it to be. But I hope you are getting something out of this right here. Okay. So any other questions at all? Because the rest of the problems I thought were straightforward, but you know, a lot of times until you do the problems, you won't get them. So I want to do at least one more problem and see how you guys cope with it. I'm going to do 3.49. Actually, let me do one prior to that. I'm going to ask you how to do it. Suppose this was a quiz. Are you ready? Just suppose that isn't a quiz. But if it was a quiz and I asked you this, suppose I gave you an electric, or I give you a voltage. V is equal to, yeah, say it's x squared plus 5y z cubed. That's the voltage. It's an odd voltage, admittedly. It's a fictitious voltage. I don't think it can exist. But that's the voltage, right?
Mhm.
And I asked you for the electric field. How do you get the electric field?
It's the negative gradient of voltage.
All right. So let's do it. What's minus the gradient of that?
2x plus.
2x.
Oh no, minus 2x minus 2x ax.
No, just leave the minus sign out in front. 2x ax, right? Don't forget the ax, correct? Keep
Mhm.
going. You're right.
5z cubed ay
Right.
ay, yeah,
That's right. Keep going.
and
That's ay.
15yz squared
No,
az.
right.
Yeah.
Az. All right. So that's the electric field vector form, right?
Mhm.
And if I asked you where the electric field is zero, how would you get it? There may be multiple points, but what would you do? Just by looking, guys. One point where the electric field is zero. Just take a look.
Origin.
Yeah, x, y, z equals zero, just by looking. If I want ex to be zero, put x equals zero. If I want ey to be zero, put z equals zero. This is x. And if I want az to be zero, you could put z or y. Matter of fact, y wouldn't matter as long as z is zero. Do y'all follow me?
Mhm.
And if I asked you where it's a maximum, you're going to find yourself looking and saying, huh? Well, it's at infinities. At z equals infinity, it's going to a maximum. At y it goes to infinity, it goes to a maximum, and at x. But this is fictitious, a maximum magnitude, by the way, not necessarily the positive direction. Do y'all follow me, class?
Yes.
So anyway, that's just something to keep in mind. So another one I want to do, did I assign 3.49 to you?
No, you did not.
This is a cool problem. All right, suppose a 6 meter diameter ring. So here and lies in the XY plane. So I'm going to try to draw this for you. So here, let's see how you guys do this one. This is a good problem. That's not drawn very well, but you get the idea. So if I have this is X, this is Y. This has a radius A of 3 meters. And here's the z-axis right here. And they want determine the potential difference VHO between the point 004. So here's a point. It's 004. It's on the z-axis. And the origin. This is a point 000. And they want the voltage difference, right? They want delta V. You with me, class?
Mhm.
And he says find the electric field. You don't need to find the electric field. Here's why. This is a point. This is a point. Remember I said VBA is equal to VB minus VA. Do you all remember that?
Yes.
Now, VB and VA are measured with respect to a reference. So you can have the reference voltage be at infinity and make it zero because that's a finite amount of charge. Do y'all follow me? That's a finite amount of charge. Do you agree with this?
Yes.
That's what we just did with the voltage for this one, for the ring. I gave it to you earlier. So this has a certain charge density. What is it? So we got rho L is equal to 5, I think it is, 5 nanocoulombs per meter, right? Now, remember I said for any given loop, this is earlier, any given loop at all, with a given charge density rho L, a given radius, and I called it rho, I think, in there, and at a given height z, I said the voltage on the z-axis, V of z, would be equal to, that's going to be rho L over 2 epsilon naught, if you remember this. And then I put this down. That's on the first page of notes. Or second page, no, first page of notes I have. And it's times rho. And it's over square root of rho squared plus z squared. Y'all remember that class? Take a moment. Look back at your notes.
This is for the voltage of a ring.
Of a ring on the z-axis, but this is going to be just a ring with a charge density rho L. I want to make sure everybody can see it. Look back at your notes. I just did this one, right? Do you remember we got the differential voltage and integrated to get the voltage for a given ring?
Yes.
Take a moment, people. Make sure you can see this because this is a good problem. This is the kind of stuff I ask about. That's the reason I'm talking about.
Is this something we should inherently know then, or should we be able to derive it?
I would know this one. It's so valuable because it's used. I mean, you can derive it, you know.
Yeah.
I'll give you a tip the way I'm getting this. If you just put all, well, now I had to do the integration, so I'm not going to say that, but you all follow me what I'm doing here, right?
Mm-hmm.
Here's a trick to this, by the way. If you take a look at any point on this wire, it's the same distance away. I mean, around this loop to this point Z, right?
Yes.
You all agree with that? Now watch. If I want that voltage, what I can do is say simply, since this distance is constant to this point, I can take all the charge and just locate it at one point. And that charge would be simply 2 pi rho times the charge density. That's all the charge. Do y'all follow me?
Yes.
Just divide that by 4 pi epsilon naught distance to this point. That distance to the point is going to be square root of z squared plus rho squared. And lo and behold, you get the voltage at that point because the distance from all these, the distance from the charge anywhere on that loop is the same. So I can cancel that, and I simply get rho L over 2 epsilon naught, and it's divided by square root of z squared plus rho squared. End of story. Y'all with me?
Mm-hmm.
That's how I do these things most of the time. So that I don't, go around memorizing formulas. I learn formulas by use, but you'll see obvious things that clue you in on how to do it. So now, why is that not focused? But there we go. Now, if you've got that, can't we get just the voltage here minus the voltage here? Follow me? Of the voltage at this point minus the voltage at this point, that would be the voltage difference, class.
Yes.
All right, so what I need is V of Z equals what, 4 or something like that? What did he say?
Yeah. At 4 and then minus at 0.
All right, so VZ of 4 minus VZ equals 0. Now I'm going to clue you on this. This is going to be negative, all right, because a voltage at infinity is 0 and it's going to be negative. So what is VZ of 4? Take this and stick in 4, right? Z is 4. We know rho is given. The radius of that is 3 meters, right?
Mm-hmm.
Or A is 3 meters. I'm sorry. Y'all follow me. This would be the radius rho. Say is 3 meters. So if you come here and you look at this, what I can do is take rho L and 2 epsilon naught out the front before I do the subtraction. This would be the delta V. And the delta V itself would be rho, the distance is 3. The charge density is 5 times 10 to the minus 9th, right? Then I have 2 epsilon naught. You can put down as, I'm going to just do as 1 over 8.854 times 10 to the minus 12th. That's an approximation. That's 2 epsilon naught. Then I'm going to go ahead. Now I have to take 1 over, it's the square root of 4 squared plus 3 squared minus 1 over the square root. And here it's at z equals 0. So it's just 3 squared. And anybody got a calculator? I can do this on one note. I'm gonna go ahead and do it, but let's see if Wentworth's book gets the same answer. So where's my, oh gosh, the thing went down again. Give me 1 second. I gotta use Global Protect, not my favorite app. By the way, I was up quite a bit last night because my dog was barking. Oh, I mean, she doesn't like, or not barking, but whimpering. My dog does not like storms, the thunder and stuff. And she was up, oh my, half the night, it seemed like. Give me 1 second. I know if you're calculating it, just tell me what you
Yeah.
get. I got to do this thing.
I got minus 113, which is what he got to.
Oh, did he? Okay.
Yeah.
Okay, hold on. Where's my phone? This is that two-factor stuff I have to do. Now I can go through and get. I should have had this up earlier, but I had all these software updates. I still have more to do. Okay, hang on. All right, it should work. Come on. No. Oh, is it on now? I got it. I'll take your word for it. It's the right answer.
Yeah, it is.
All right. Everybody
Yeah, I got
okay with
minus
this one?
113 as well, so I think that's right.
All right, I got math cat up, but anyway, enough of that. So now the next thing we're going to talk about, we did potential, and really, if you have the voltage in terms of the variables, it has to be in terms of the variations. It can't be a constant. But in terms of X, Y, and Z, and you want the electric field, you take minus the gradient. Overs. Voltage is much easier to calculate in general from charge distributions than electric fields. So if you calculate the voltage and leave it in terms of the variables, then take the gradient, minus the gradient, you can easily get the electric field. It's usually a whole lot quicker than doing integrations of 3 components. Next thing we're going to talk about is conductors. In the book, it's on page, how many people do we have here? 8 or 7, really. We're missing somebody. I think we're missing Chase, unless he jumped on, and we're missing the fella 8, whatever his name is. So we're missing 2. I'm glad you're recording. Thank you. So I think you've had resistance. You've had this in your I don't even know what course it was. Probably in physics for sure, but you might have had in engineering too. I mean, this is going to be the calculating the resistance of a material based on the constitutive parameters stuff. Greek, I guess it's pronounced constitutive, but anyway, here's what we're going to talk about resistance. So when we're talking about resistance, you're used to seeing a resistor as shown as this, right? And I'll try to make this easy to see. Agreed, class? That is called the lumped element. It's a bulk parameter. It doesn't matter if what's causing this is a light bulb or a piece of carbon or anything else. geometry has no bearing on this. It's a single value and it's in ohms. And I think everybody knows that. So how do you calculate resistance from materials? Well, we'll start with the simplest thing. If you have a carbon tube or any material, and we assume it's got a certain length, just write this down. I'll try to make it as easy as possible. And we assume it has a certain radius. This is going to be a cylindrical, it looks like a wire, a radius A. And we can say that the cross-sectional area of this would be equal to pi A squared. Now that should make perfect sense. Did you all with me?
Yep.
Yeah.
All right. Now, if you take this, and we're going to assume a couple things. I like to do this way to show you what you're actually thinking or should be thinking. If you hook the battery with a voltage V across those things, and we assume a current is driven through it, I. And we assume furthermore that the current will uniformly split or distribute itself over this surface to get a constant value of current density. Now I have to talk in terms of the values. So something I'm going to say is there's a material parameter called sigma, and sigma has the units of 1 over ohm meters, or sometimes they call it just Siemens per meter. Siemens is 1 over ohms. Those are the units. If you have this, and this is the conductivity, then the actual current density is symboled as J. So I'm going to write this down here. J is the current density. And what J really is, if you take I and you assume it's uniformly distributed over here and I is flowing in this direction, then you can say that I, or that J is simply going to be equal. It is a vector, so I'll call this the AZ direction. J is simply the value of I over the area and a vector that's probably, or that's actually flowing in. So it'd be I, for my case, over pi A squared. And here it would be in the AZ direction. The units of J are amps per meter squared. Have you heard of J, the current density, before in that class?
Yeah.
Okay, in physics?
Mostly, yeah.
I don't know why that autofocus is so hard, but it is. Okay. Now, J itself is also equal to sigma times the electric field, and this is an important one. This is one that's very important. You can get J by just finding the current, dividing by the surface area it's flowing through. So if we assume I, and here's how we're going to do this. We're going to assume I, then we're going to get J. Once we have J, we're going to get the electric field. And the way we're going to get it is the electric field will be equal to J divided by sigma. Make sense to everybody?
Mm-hmm.
Now, after the electric field, we're going to get voltage by integrating the electric field dot dl over, you can say from 0 to L. That voltage will always be a strict positive. That's a nice thing, because we're talking about a value of voltage that would be developed or across 2 points. And once we have this V, to get the resistance R, we simply do V over I. That should make sense. So we assume I, we get J, we find E, then we get V by integrating it. And that has to be equal to V divided by the I we assumed. Make sense to everybody?
Mm-hmm.
Take a moment, just think about it. It should make perfect logical sense. Okay, now we've got that. Next thing we can say is, if I assumed I, and I'm going to continue with this one, I've got J right here. I can get E right here. So E itself, for this particular problem that I'm showing you, let me move it up a little. That value of E right here is going to be J, so it's equal to I over pi A squared divided by sigma. And that will be in volts per meter. And it is in the AZ direction for this one. Y'all follow me? Can y'all follow me on this one?
Yeah.
I got another one. I've been getting crazy. Light rain soon. If anybody takes a look at the weather, tell me if we're going to get any bad weather in the next hour. So now that I have that, I have to integrate that. And this will always be positive. This is the nice thing about it. When I integrate E dot dl, you can forget about the signage in terms of it's negative or positive, because with resistance, resistance is always positive. This voltage is going to have a positive value. If it's negative, you make it positive. It's going to go from 0 to L. When I do that, I go from 0 to L of that value of the electric field, which is I over pi A squared sigma in the AZ direction dot DZ AZ. Well, that's just the integral of DZ from 0 to L is just L. So this voltage right here is equal to the current that we're assuming times L over the area pi A squared divided by sigma. Finally, we can get the resistance, which is V over I. Y'all know that. That's Ohm's law in the most simple sense. And you can see it's never a function of the current, never a function of voltage for any material that's not active, or like a battery, it's different, or any kind of nonlinear material will be different. But this is for linear standard materials like carbon and stuff like this. It becomes L divided by pi A squared sigma. And that's the resistance of a wire, you might say, of a given conductivity sigma. Can you all follow the rational way of thinking about this, guys? Everybody?
Yeah, I'm good.
Zach, you getting it? All right. And I'm assuming Hayden and Jonathan, Jackson. All right. Everybody else okay with this? Any questions? All right. Now, here's the deal. Circle this one thing right here. You see this pi A squared? That's simply the cross-sectional area. All right. That cross-sectional area right there, if you have a square wire, as long as the cross-section is constant, or an elliptical wire, it doesn't matter. As long as the thing has the same cross-section over the length, this is how you calculate resistance. Now, with wires, it's particularly important, or conduits. You can have wires that are hollow. Basically, they have an outer radius and an inner radius that's close to the outer radius and it's hollow. So there, it's the cross-sectional area of that hollow section. Can you all follow me?
Yes.
And that's it. And it's always resistance for wires are always proportional to the length of wire, inversely proportional to the cross-sectional area, and inversely proportional to the conductivity. Now, you've said you've heard of conductivity before. So I'm going to ask you a question that most people don't know off the top of your head unless you worked in this area. So what's the conductivity of air right here? Any idea? I mean, at sea level air right here in Auburn, Alabama, or probably most places in North America with the exception of the deserts. Anybody? If you don't know, don't worry about it. It's about 10 to the minus 14th, 10 to the minus 13th, 1 over ohm meters. It's just about an insulator. Y'all with me, class? Just about an insulator. If you think about that, 1 over that is 10 to the 14th, 10 to the 15th. So if we had a tube of air and we asked the resistance between one end and the other, if it was metallized, it would be enormous, like 10 to the 15, 10 to the 16 ohms, which is basically an open circuit. But that gives you an idea of the magnitude. Now, what do you think the conductivity for copper is? Does anybody have an idea?
Be quite hype.
Yeah, you want to take a guess? Maybe you don't have a good feel for it.
amount.
Copper, standard copper, not alloy, standard copper, amorphous copper, that's pure, is about 5.8 times 10 to the 7th Siemens per meter, or 5.8 times 10 to the 7th to 1 over ohm meters. One thing you see is there's what? From just air to copper, there's
10 to the 20th, 19th.
21st, 10 to the 21st to 10 to the 22nd orders of magnitude. I mean, there's a real, I mean, not orders of magnitude. That's the actual magnitude difference. Orders of magnitude is about 21 to 22 orders of magnitude. That's an enormous amount, but that gives you an idea, at least the possible range. There's something else called a superconductor. Have you all heard of that? Class? Or no? You've heard of high temperature superconductors? Anything? No?
Yeah.
Well, you should be at least aware of them. High temperature superconductors, some people say, well, they have a conductivity of infinity. That's kind of true. It actually effectively seems to be that, but the high temperature superconductors, by definition, do not let a magnetic field penetrate it. So because of that, and you'll see this later, the current densities will be developed so that it prohibits a magnetic field from entering. But it looks like an infinite conductivity. Now, without getting in too much detail of this, there is a limit to the current density that can be present before the superconducting effect fails. In other words, it has a maximum current density. Just be aware of this, because some of you are going to go to job interviews. I want to make sure I at least tell you the basics about it. You can think about it as a superconductor as long as the current density doesn't get too high. And we'll talk about that a little bit later when we do magnetics. So that's current density in a nutshell. And I might as well, while I'm at it, just say a couple other things. Now, please write this down. This is important. The first thing is, when you have a given current density, you also have a given power density. So the power density, Dr. Wentworth does not break this out real clearly. The power density, since it's a density, is equal to simply sigma. It's really J times E, if you do it this way. If you look at the unit, and the units will be watts per meter cube. If you take a look at this, J has units of amps per meter squared, and E has units of volts per meter. So you get amp, right? Amp volts per meter squared, and amp volt is a watt. Y'all agree with that, class?
Mm-hmm.
So here's the way power density is usually written. They call it P, and I'm just going to call it P sub D, power density. Normally they put sigma E for J, and they'll put it sigma times magnitude of E squared. That would be in watts per meter cube. That's power density. And again, this is power density. Now, when we have electrostatic fields, we also have an electrostatic energy density. So this is 2, write it down, the electrostatic energy density. That's usually given the symbol small WE. W, work and energy are interchanged, but this is a density too. I'll call it WD. It doesn't matter the symbol. And the electrostatic energy density, I'm going to use it this way, will be equal to 1/2, and then it's epsilon times the magnitude, or times magnitude of E squared. And this is going to be joules per meter cubed. Now, the reason I'm showing you this right now is I want to make sure that you know if current is flowing, you're dissipating power in any material. And this is how much power you would be dissipating right here. It would be J times E, or it would be this. This is the power that you're dissipating per meter cubed. This is the energy that's stored in an actual material per meter cube. And I might add right now, we haven't hit capacitors yet, but that value of epsilon is epsilon relative epsilon naught. Might as well write this down. Now, when epsilon relative gets gets very, very large, you can store a lot of energy in a parallel plate capacitor with a relatively low voltage. Those are called supercapacitors. Have you all heard of supercapacitors, class?
I have not.
Nobody? Well, you can look it up on Google. Supercapacitors are very interesting, and here's why. Suppose you have something that's a supercapacitor. Normally, if you think about a capacitance, and I know this is a little bit advanced. I mean, we haven't done this. If you have a separation distance D and the surface area A, and it's got a value epsilon there, capacitance is equal to epsilon A over D. You're just going to have to go with me on that, over D. Now, the energy stored in a capacitor is 1/2 CV squared. If you look at that, that's 1/2, that's C, so it's epsilon A over D and V squared. Now, I'm going to do something. You don't have to follow me. You don't have to write that down. I just want you to see something. So, sorry. When I look at omega E, I can take out 1/2 A epsilon naught D and V squared. Take the 1/2, then I'm going to take epsilon naught A over D and then V squared out in front and multiply it by epsilon relative. This would be the amount of energy that the capacitor can store if it was filled with air. Y'all know what a parallel plate capacitor is, right?
Yes.
Now I got thunder hitting me right here. All right, well, if you look at this epsilon relative, if you could make that 50,000, you could store 50,000 times as much energy. Basically, what would take 50,000 times the space to store the energy can do in just a small amount, 150. So why do you want to store all that energy? Well, how many have actually had to try to start a car in very cold weather here? Anybody? What do you need? You need more current, right? I mean, your battery's current delivering ability goes down as temperature goes down. It just does. If you get it really cold, you can't start your car because there's not enough current to drive the actual motor that's turning it. So one of the things I'm not sure what motor companies use this right now. They put these supercapacitors that are very low voltage, 14 volts, maybe 12, 14. It's like the voltage on your car battery. And they store an astronomical amount of charge. Charge stored is QV. Sorry, that's my bad. Charge stored is really going to be equal CV. Charge is equal to capacitance times voltage. If this thing is huge, you can store a whole lot of charge. And what is current? It's equal to dq dt. So once you turn the crank on your car, this will be in parallel with your battery, but it'll start bleeding current that will be very large and as needed to start your car in cold weather. That's one of the applications of these supercapacitors. I'm trying to throw a few things out here, but that's why epsilon becomes important. Because the larger the value of epsilon, the larger the amount of energy can store in a very constrained volume. And those are exotic materials that we'll talk about later. But I had to throw this out to at least whet your appetite, because now, oh boy, now I think I'm almost out of time. I got a few minutes. I'm going to do some problems with resistance, but I tell you, the next thing I'm going to do, and that's the reason I did this, is capacitance. Now, I've never done it this way, but I think I'm going to do it this way. So you all know what capacitors are, right? You've had this in physics, correct, class?
Mm-hmm.
What's a capacitor basically to you? I mean, in your own words, anybody? It's what? It's just we make capacitors. I don't know if you guys ever did this. If you go get some wax paper and aluminum foil, you put about a 2-foot section of aluminum foil down. Then you put a pair of wax paper on it that's large enough so that it extends over the edges of the aluminum foil, and you just roll it up like so. I mean, actually, I'm sorry, don't roll it up like that. Then you put another piece of aluminum foil on that's insulated from the first piece. Take that and roll it up like you would anything, a rug or anything like that, roll it up, and then go ahead. Remember that wax paper is fairly small. It looks like a parallel plate capacitor. You just rolled it up. Then take it and charge it up with like a, I don't know, 10-volt battery, something like that, 12 volts, whatever. Charge the inner and outer one. Remember, they're insulated. And go ahead and take that thing, and if you discharge it to a resistor, a fairly large resistor, and looked at the voltage, you'll see it stores a fair amount of charge. That's what a capacitor is. Two conducting surfaces separated by any kind of dielectric. And it stores electrostatic energy by inducing plus or minus charges of same magnitude, opposite sign on plates. So for capacitors, I'm just about out of time. I want to just tell you in the book where they are. And I want to mention that it parallels the stuff with the with resistors. We're going to be talking about this. So I'll do boundary conditions at another time, but I'm going to show you this capacitor business. He has the electrostatic energy on page 198 if you want to know where it is. But if you look on your book on page 194, he talks about capacitance. Capacitance is Q over V, or charge is capacitance times voltage. And I think at least most of you have seen, you had to have seen this in physics. It's essential. If you're going to be an electrical and computer engineer, you should know this very well. So come over here, and there he's going to go through how do you calculate capacitance. Just like we calculate resistance, you assume something. You assume a charge or a voltage. Normally it's charge. Then from the charge, you get the D field, not E field. From there, you get the D field. From the D field, you get the E field. From the E field, you go ahead and you integrate the E field between the surfaces to get the voltage. Then you go back to capacitance is Q over V. I'm gonna do these things next time we meet, which will be Friday, and I'm going to give you some reading and homework problems related to resistance and capacitance, and we'll wrap this up. And then, since we have Monday off, we'll get a quiz on Wednesday. Okay.
Okay.
Everybody okay? Any questions? You can. I'll hang around. Consider this my office hour. I wish I knew where the other guys were. Y'all got that link, right?
Yeah.
Yeah.
I don't know. Let me just see. Are they here? And I'm not seeing them. I'm not seeing a whole bunch of people. Andrew, you're here. Ming Lee, Aiden, Jonathan, Jack.